In the previous lecture, we had derived, or first we had defined the concept of a transfer function and derived transfer functions of three examples. One of them was that of the DC motor, where the input was the voltage and output was the angular velocity that the motor generates. We had followed the standard steps of first writing down the governing equations, which could be differential equations, and then converting those differential equations into Laplace transform and eventually writing down the transfer function. Before we ended the lecture, we asked ourselves a question. Can we draw the block diagram representation of example 3, the DC motor, as systems in cascade and feedback? Because after the example, we had seen few special cases of how systems behave in cascade, in series, or in parallel, in feedback, with some kind of beautiful properties of deriving the overall transfer function. Hello and welcome to this lecture number 2 of module 3 of the course on control engineering. We will continue our discussion on transfer function of dynamic systems and derive transfer functions of few more examples. Before that, we will again start to draw the block diagram of a DC motor as transfer functions or blocks in cascade or in feedback. Okay, so what is the governing equations or what are the governing principles? We started off with the voltage source resulting in a back EMF, and this back EMF is related to the omega, and the current in the armature is also related to the torque. Okay, so let us write down each of these equations. So first is I had V was equal to L di by dt plus R times I plus the back EMF. Okay, so this I can write as V minus E as, let me write in the Laplace domain, right? S times L plus R times I of S. So all this here is in the Laplacian domain. Let me also call this as, say, E of S. So the first thing we start, okay, so I have V, which is my input voltage. This will be with a plus sign, this is a minus sign. Here comes the signal E of S. This goes, so if I look at output of this as the current, this goes through 1 over S times L plus R and gives me I of S at the output. What we know is that the current and the torque are related in the following way, that T was equal to KT times I. So this I gets multiplied by KT to generate the torque. Okay, and then this torque goes through, okay, what is T? T is the moment of inertia and the frictional component. Okay, so if the final output is omega, what is the relation that gives me, what is the thing that relates T and omega? I just look at here, right? So if I write down the Laplace transform of this will be T of S is S times J plus B. Let me call this capital omega of S, which means T multiplied by 1 over S 1 over Sj plus B gives me omega. Okay, how to close this loop now? We see that there is a nice relationship between the back EMF, E or EB, whatever notation we use. This is related through the notion that omega times Kb is E. Okay, so this omega goes through KB and gets me this E. Okay, now we are in a good shape, right? So there are these three things in series. We choose a different color. This three things in series will now become, I just write it in red, KT over SL plus R Sj plus B. Okay, now we have this in the standard form, right? So I just simplify this. Everything inside here becomes, okay. So in the forward loop, now I have this becomes K T over SL plus R Sj plus B. And what we had seen is if I have a G and a H in feedback with the reference and the output, Y over R was equal to G over 1 plus GH. Okay, so this will now become my G, this will become my H to give my overall transfer function. Okay, so this is the block diagram representation of the system that we had seen earlier, which was the busy mode. Okay, so what are the properties of this transfer function? The first property, or the first important property, is that the transfer function is independent of the magnitude and the nature of input. So it is not really input, even though it's a ratio of the output versus the input, it's largely a system property, right? And using this transfer function, I can study response of the system to uh, various kinds of inputs and therefore understand the system better. However, the transfer function does not provide any information concerning the physical structure of the system. When I say this, it means that two physical systems can have the same transfer function. Okay, so let us derive the transfer function for this mass spring damper system that is shown here. Okay, how do I do the transfer function? First, write down as a mechanical system. I can write down a nice free body diagram for this. I have this as my mass. Certain force acts on the system. It has a frictional component and it has a spring component also with the motion going in this direction. Okay, if I write down the force balance, F will be, or F, so what will result in the motion is Fx double dot. This comes because of F, but then there is the frictional force and also the spring pulling it back. Or in other words, I can add this as F equal to mx double dot plus bx dot plus kx. I can write this in Laplacian domain as f of s is s square m s times b plus k x of s. If x is the output and the force is the input, I have a nice transfer function of this one. S square m plus sb plus k. Okay. Now in the special case when m equal to, okay, it should be k. When m is equal to k equal to b equal to 1, I get a transfer function which is like this, 1 over s square plus s plus 1. I can go back to the RLC circuit example of module 3 lecture 1. This is the example 2. With r equal to l equal to c equal to 1, I get the same transfer function, right? which kind of justifies the statement that two physical systems, in this case, the mass spring dampered system and the RLC circuit, they had a voltage Vi. I was measuring the voltage across the capacitor as the output. Okay, these are two physical systems. They have the same transfer function. So it doesn't really give me an information of what kind of system is it. Is it a mechanical system, electrical system, a simple pendulum, a DC motor, and so on. Okay, so few more examples let's do, right? So some very simple, we make a lot of assumptions here, but this is good for us to build up our understanding. Transfer functions for a simple cruise control. So the coordinates in the car position is x, and the distance from the reference line is shown as positive to the right. So and this is the direction of motion. And what I want to find is have the input as a force, find the transfer function between u and the velocity. I don't want to look at position as the output, but I'm interested in at what speed my car is traveling. Okay, so how do I do this? Again, this is also a slightly departure that it's just not always a position that could be the output. It can be the velocity also. Okay, so this is nice. I just write down the Newton's second laws and the force balance equations of V dot. So it'll still be the same, right? So m x double dot plus b x dot equal to u, right? And then now since I'm looking at velocity, my force will, so this equation will be m times velocity dot for the acceleration plus b times the velocity is u. Okay, then I do a Laplace on both sides, so I get m s plus b v of s is u of s, and resulting in the transfer function which relates the output, which is the velocity, to the input, which is the force, as 1 over ms plus b. Okay, so of an automobile suspension, right? When I drive a car, what we see is that roads are never perfect. Especially if you look at cities in India, there will be a lot of potholes, there will be bumpy rides, and so on. Experience bumps and these bumps and dips on the roads is not very pleasant while we are either driving a car or even sitting in the car. And while driving also, one needs to ensure that there is enough friction between the tire and the road. Again, it's ensuring a comfortable ride. It is good for steering position and so on. What is the control problem? The control problem, I show a little animation which is from a design from a small vehicle that we built in our lab to test control to test connected and autonomous vehicles. You see, so this little bump there could be like a series of speed breakers. What happens is that the car should continue maneuvering through that, and also it should not kind of just wobble or make things unstable or even uncomfortable for the passenger. How do we design these things? It's also, if you look at these are also normally referred to as shock absorbers. So what goes under this behind this design, and what is the problem here? Again, when I talk of friction, just imagine driving a car on ice where there is no friction. You brake, you steer. Many of those actions don't work because there is no friction, right? The control problem, therefore, is to design a system. System here is a controller that responds to road irregularities and external forces affecting ride comfort and vehicle stability, which means road isolation. My car should be independent, or the comfort level should be independent of bumps or dips on the road. Also, the tires need to be kept in contact with the ground. And this is what ensures you can steer, you can brake, and accelerate safely. And also, if there's a curved path, the vehicle should travel the curved path while minimizing the body roll. Okay, this is a nice control problem. I'll update a small video on this explaining the construction or the mechanical construction of this. But what we will be interested here is how do we design such a system? How do we design such a system which provides me road isolation, road holding, and also cornering. Okay, so this is how it is. It's again comprises of a mass spring and a damper system. There will be two masses x, with x and y with reference direction as shown. So x and y are the displacements of the masses from their equilibrium conditions, and we define x to be the distance from the equilibrium. A force will result if either the road surface has a bump. So the input here will be the nature of the road. Say maybe a bump, a speed breaker, a pothole, or whatever. Right. So this is the input is the reference. So is the R, which is the what is happening in the road, and output is how the vehicle reacts, right? How the X changes with respect to this change in R. So and eventually I will be interested now is in the overall displacement is Y with the input being R. Okay, this is the mechanical construction of now. Okay, now I would want to have the dynamics of this suspension system to describe how this system responds to road irregularities and external forces. So once I know how the system responds to these road irregularities and external forces, I can provide enough compensation or control methods to provide the right comfort and also vehicle stability. Okay, so this is what this does, right? So again, I just do the free body diagrams. I have a spring here with this forces acting in this direction, ks y minus x, by uh, by minus. This should also be a dot here. These are the frictional forces. This is the spring kw, which is acting downwards. Similarly, I can do it for mass m2 with this y direction. So this will be in the opposite direction, ks y minus x, and b. Okay, I think this dot is hidden in the bracket, but there should be a dot here, y dot minus x dot. Okay, now this is in familiar terrain. The physics tells me how to draw the free body diagrams, and then go about writing down the equations of it. Okay, so this is the equation number one comes from writing down this balance law. Equation number two comes from writing down this balance law, a simple exercise. Then, so the steps for deriving transfer function are first write down the equations of the system, then do the Laplace transform of this, and then finally derive the transfer function. Okay, I'm skipping the steps here, but what you can do is fill in the blanks here. Okay, fill in the blanks by just writing down the appropriate steps. So just straightforward, just take Laplace transforms of both sides, and then check how the output will look like. Okay, so some complex looking systems can also be modeled simply, right? So I'm looking at the satellite attitude control model, where the input is the control force which comes from the reaction jets that produce a moment about the center of mass. Okay, and there may also be small disturbance movements on the satellites coming from here, which arise primarily from a lot of solar pressure acting on or any asymmetry in the solar panels. Output is the angle theta that describes the satellite orientation. So what is the math behind this? The sum of external movement around the center of mass is inertia times the angular acceleration. Just simple rotational motion thing. So input u of t, this is fc times d, which is the force control force which comes from the reaction jet. This should be equal to I theta double dot. So H of S again is simply the output theta over U is just a good simple second order system. Okay, this is nice. Another simpler one. So again, in a very familiar terrain is how do we look at transfer functions of electrical circuits? Okay, I'll do one more example here. I have an input voltage, which is this, and an output voltage. Just R and C circuit constructed slightly in a different way. So I'm looking at VO as the output, VI as the input. Okay, so I just start with node 2. I write down my KCL, which would be okay. So assuming all the references and the signs as here, I will have a negative of V1 minus V2 over R1, this corresponding to this element. Then I have again V2 minus V3 corresponding to this, plus C dV1 by d. So this is V2. The current here would be C1 dV2 by dt. So the sum of all currents at node 2 is 0. Similarly, I have another node here. Uh, Sum of currents of all at node 3 is also 0. What is the currents that come through node 3? That is coming from R2 and also coming from C2. Okay. In C2, so I have V3. The potential difference is V3 minus V1, and with the capacitor, which is C D, the potential difference over D3. Again, fill in the steps to get to this transfer function. Okay, so fill in the steps to the. So again, I will not go into the details of this. I will just let you fill in the steps, and this should be also easy to compute. Okay, another familiar is the world of operational amplifiers. I have input applied voltage, output applied voltage. I simply apply the KCL at this particular node. I have that okay, the summation of all currents is equal to 0. Results in again a simple equation of current through a resistor, equating that through a current through a capacitor, and this gives me a nice looking transfer function. Again, assuming that this is equal to 0, that's the assumption, right? When we derive transfer function, that all the initial conditions are 0. Again, resulting in a first order system of this form. Okay, one step further, how do I look at mechanical systems with gears? Okay, so what is happening here is so I have okay, I have a gear with a certain teeth ratio, N1 and N2, and in our week one lectures we saw how gears are modeled as per this numbers. Okay, so with some gear ratio N. Okay, I assume here that the gear ratio N1 by N2 is equal to N. Okay, so there's an input torque which generates. So I have a servo motor whose output torque is Tm, which is attached to gear one, and also this gear one is meshed to gear two, and the angle theta two describes its position. Okay, so there is some inertia for gear one, which is called J1, and there is inertia for the gear two, which is called J2. Similarly, there'll be frictional components for the gear one and gear two. What we want to do is to determine the transfer function between this applied torque and the angle that is generated here at J2. Call this as theta 2. Okay, again, this is nice. We just use the standard equations for rotational motion. So I have so this Tm. Okay, so this Tm is the input torque. Okay, this Tm, this goes through. So Tm starts here. What results here is T1. The torque which transmits to the gear is T1. What happens in between is that there will be some dynamics associated with the shaft here itself, right? So this is so I have the difference of those torques are captured by J1 theta 1 dot and J2 theta 2 dot. Like, so it starts with Tm. This Tm goes through my J1 and B1 and gives me a T1. Okay, now on the other side I have T2, which relates J2 theta 2 and B2. This is a standard relation. The T2 is J2 theta 2 double dot and B2 theta 2 dot. Okay, now replacing this with the gear ratio N. So, and the torque T2 with like this. This again just comes from this how the ratios are related to each other. I'm just eliminating. Uh, 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 so I'm just writing everything in terms of Tm and theta 2. That is what my transfer function is to be derived, right? So my input is Tm, output is theta 2. I'll just eliminate everything else over here. So so just look at this expression here. I am eliminating. Uh, so theta 1 will be equal to n theta 2. I also would want to eliminate T2 will be equal to n T1 and so on. Okay. So again, fill in the steps. To get to an answer of this form. Again, this is kind of pretty straightforward of what is happening here. Just simple mathematical or simple algebraic substitutions to get a transfer function for a system. Now with gears, the key here is how this n square term appears here. We will use this n square term into a more complex example where I have a position control system where I have to maintain a certain desired theta r. This is my actual position system, which is goes through a motor again via a gear, and this should be my output. Okay, we will see this, and also another question that we will answer, we will try to answer here is if I have these two RC filters in series, will the overall transfer function be, can I look at this as system 1? Can I look at this as system 2? Think of them as cascade of system 1 and system 2 and say that the overall transfer function therefore should be 1 over SR1C1 times 1. So 1 over 1 plus, this is a transfer function of S1. This is a transfer function of S2. Is this correct? Right. So we will ask this question, is this the overall transfer function of the system? And then how will we handle a complex problem like this where it's a position control system with a feedback involved? Okay, we'll take a pause here. We will just remember what we did here so far and try to solve a couple more complex examples and learn one important concept of what we should be careful of while we are deriving transfer functions. That's coming up in the next lecture. Okay, welcome back to this continuation of lecture number 2 of module 3 of the course on control engineering. We look at a little more complex systems here, and so the idea here is to drive a system to some kind of a desired angular position theta L. So this comes via some gear mechanism here, where just before the gear there is a motor which generates an angle theta 1. Theta m and theta n, theta m and theta l are related via the gear ratio 1:1:n. This theta l is measured by a device called a potentiometer, which will convert the position into appropriate appropriate voltage. And there's also an input potentiometer which will measure this theta r and convert it into an appropriate voltage. Okay, what is the mechanism here? What is the steady state position of the loop, right? In the steady state position, which means theta c equal to theta r, and both of these are equal, there is no potential difference. The E therefore is 0, EA is 0. EA is the voltage supplied to the motor. If the voltage supplied to the motor is 0, nothing happens. Okay, so we are at equilibrium, we are at peace because we know that our motor or our output here of this position control system is at theta L. Okay, so the mechanism is now as follows. So at steady state position, E is 0 as we just saw, and any change in the command theta r, let's say I want to change the reference to say something else. Any change in the command theta r, say maybe this is say this is 5 degrees. We set this to 5 degrees and say this achieves 5 degrees, which means theta L will be equal to theta r, E is 0, and so on. Let's say this changes from 15, theta r changes from 5 to 15. This also must appropriately change, right? So in this case, when the command signal theta r changes, it introduces an error. And then this error will now produce some voltage here, because theta c is not equal to theta r. E is not equal to 0. Therefore, EA is not equal to 0. And when EA is not equal to 0, it will drive the motor until theta c becomes equal to theta r. Okay, so what are the various constituents here? I have a armature controlled DC motor. The load is driven through a reduction gearing to amplify the torque to move the load. So that is here. We also saw how gears amplify or reduce the torque. And the angular positions are sensed both sides by a potentiometer. The position error in form of voltage is fed to an amplifier, which will generate the desired motor armature voltage EA. So the question here is derive the appropriate transfer function from theta r to theta L. Okay, let us look at each of these constituencies here, or constituents here. Okay, so at the motor end, okay, let's first see the complicated part, and then we'll come back to the simplified part. Okay, so I will first concentrate on this part. So this is where all the action is happening. Okay, in this place where all the action is happening. Okay, so I have JL, I have J, whatever the torque is coming from the motor. So the motor is now driving JL via these gears, and they have their own own inertias and own friction components, JM, FM, JL, and FF. So the overall J that the motor would experience would be Jm, what is here, and what is also driving the load. That will be also with a factor of n square, as we saw in the previous example. Similarly, the friction component will also see the friction of the motor, then it goes through the gear to drive the load. This will be okay. Now this is nice. So the motor experiences J and F as the load. Again, we'll go to where we started off in today's in the first example of lecture 3 is to derive or write down the overall transfer function of a DC motor. Okay, so I have now J is the overall J that my motor experiences. F is Fm plus n square FL. Okay, so I have input to the motor. This input produces, as always, a back EMF. We call this E in the previous lecture, or in the previous example. Also note that here I only have RA. There is no LA, no inductance of the motor winding. Okay, so no inductance of the motor winding, so L disappears. So if I just do sequentially of what I did, so I had so here I had the component of 1 over SL plus R. This will only become 1 over R. This will generate the current. The current goes through a constant producing a torque. We see how we know how the torque and the current are linearly related. Torque goes through all the mechanical components 1 over Js plus F. This is the overall load of of what my motor experiences, and generating an omega m. Omega m. So where is this omega m sitting? This omega m is sitting right over here, right? Theta m. theta m dot is omega m. Okay, so now I have a transfer function now which starts from EA. Okay, so my input now is EA and the output is omega m. In that little block of that motor where I said all the action was happening. So I just do my say simple block diagram algebra. Omega ms by the input voltage to the motor is Km by tau s plus 1, where, okay, I'm just absorbing all into one constant. So Kt over R, okay, I'll call this armature resistance as Ra. I have a F plus Kt, Kb, and then the what is in the denominator is tau. Tau will be okay, J over F plus Kt Kb by Ra. Again, you can fill in all the blanks here. Okay, these computations should be easy. Okay, so where am I now? So in the process of deriving the transfer function, I have the input to the motor, which goes through this terms here, Km over tau s plus 1, generating omega m. Okay, what is omega m? Omega m is the angular velocity at the motor end. This omega m. So again, what should I derive? I should derive the transfer function from theta r to theta l. And where does theta l sit? Theta l sits here. Right now I'm here. I know omega m. Theta l sits here. Okay, so that is my final output which I want to reach. Okay, if I am given omega m, this is the angular velocity. I integrate the angular velocity to get the angular position theta m. Okay, now where am I? From here I do integration at theta m. Now I go from theta m till theta l. How are these related? These are just related via the gear ratio. So theta l and theta m are related via the gear ratio. Okay, so I just plug in the gear ratio here. This will be n to give me theta l. Okay, am I done? Well, I wanted to find out what is the transfer function between theta r and theta l. Okay, I got theta l here now. Now what should I do here? With this EA, I should be able to go backwards and somehow get to theta r here. Let's see how the mechanism works. EA comes as a result of multiplying this A with, this E with Ka. Okay, let's do that part first. EA, sorry, okay, I'll just, okay, I'll make a little space. Okay, this is my EA. This EA precedes Ka. So here will be, okay, I'll just have to make it shorter. Just okay, this box will be Km by tau s plus 1. This is my EA. Preceding EA is the amplifier, which gives me, okay, let's reverse it. So this one, this voltage E. Okay, now I have reached until E here. Okay, where does this E come from? This E is, okay, this E comes as a result of converting this. So E is a voltage, right? E is a voltage signal. whereas theta c, which is the measurement of theta L, this is the potentiometer which measures theta c, and theta r, these are angles. So what is the quantity which converts the angles into voltage? Is this Kp? Okay, so I will have, sorry, so this is my reference theta r. This is my final measurement theta r. There is a minus here. Theta r minus theta L goes through the potentiometer constant to give me a E, and then the entire thing proceeds. Okay, this is the K potentiometer constant. Okay, now I have a bunch of things here in Cascade. So let me call this entire things in Cascade. G of S will be, I have Kp, I have Ka, I have Km, I have this number N over tau prime S plus 1 and S. Okay, now the overall transfer function theta L over theta R is, if I call this G, that is G over 1 plus G. This will be, I think I'll just skip the steps, Kp, Ka, Km, N over tau S square plus S plus Ka, Kp, all these things we just go Kp, Ka, Km times N. Okay, straightforward. What have we done here, right? So if I just look at how we simplified this into get into our final solution, we just looked at these as individual systems talking to each other, right? We just started off looking at how the motor action first behaves, and from the motor action we started off with from here, and then so we started off from this block and slowly went backwards here, forwards here to build up. And then how did I derive the overall transfer function? The overall transfer function was derived just using the formulas for systems in cascade, systems in feedback, and so on. Okay, so this example is a beautiful example from the book by Nagrath and Gopal. A pretty famous book on control systems. Okay, so this is nice. I'm assuming we now know the answer. Okay, we did derive. This is done. Okay, other question which we left the last lecture was, can I write this system as cascade of two systems? Okay, so that is an easy way to write. I just look at V in, and I look at this intermediary V1. So I look at V1 by V in as one system, and then VO by V1 as second system, and overall write down what is VO by. So if I call this as G1, I call this as G2, overall VO by VI will be equal to G1, G2. And this G1, G2 are individually looks something like this. Okay, is this the answer now? Okay, we will try to answer, and whenever we are in doubt, we just go back to the basics. What are the basics of deriving a transfer function? Basics of deriving a transfer function are, write down the equations from first principles. In circuits, what are the equations that we know? These equations come from writing down Kirchhoff's voltage and current laws. By now, I assume that we know how to directly write the equations in the Laplacian domain. So here are two systems that are cascaded. This is an RC filter where V in is the input to the first system, and VO or V out is the output of the second system. Okay, so I'll write down equation V in. So something here, right? The input voltage will be the current here. Okay, the input voltage will be some current here going this way. I'll call this I1. I'll call this I2. And then we know this is all familiar terrain to write down the voltage loss. Okay, let's write down the equations of this system. Now, by now, I'm assuming we are familiar enough to write down equations in the Laplacian domain. So V in, I can write V in the Laplacian domain. There'll be some current here, R1, and something here, right? V1 or the current through C1, which will just be I1 minus I2. So if I say I1 is going in this direction and I2 is possibly going in this direction. Okay. Similarly, I can write down V out here as an expression relating C1 and R2. And finally, V out is also related to C2. Okay. So I just go here, write down these three expressions. Sorry, this should be C1 here. Okay. And then I just have these three equations. I just again kind of join the dots, write down the steps. Okay, to say, okay, V1 by V2 is now, okay, I have, this looks familiar. This also looks familiar, but there is something else here. So the answer after all this math says that is this transfer function equal to whatever we have written here? Well, the answer turns out to be no. Okay, what is happening here? And let's just argue this a little bit and also understand the physics a little bit. So the overall transfer function here is not equal to the product of transfer function of two RC circuits in cascade. Okay, this is not. So this is a transfer function of two RC circuits in cascade. But this is not the answer. This is because that whenever we derive a transfer function, we start with the assumption that while deriving a transfer function, especially for systems in series, that there is no loading, that there is no power drawn at the output of the system. And this assumption must be satisfied even while deriving transfer functions for each component in a block. So in this case, power is being drawn from the output, where the output is measured across the C1. This C1 pumps in energy to the second system, right? And therefore, this doesn't hold because there is some kind of a loading effect. So if one component is acting as a load on the other component, transfer function cannot be determined separately. Okay, so we should then write down the overall equations and then do by first principles. Okay, so what is happening here, therefore, is that the overall transfer function is not equal to the product of two RC circuits because the assumption of no loading fails when individual transfer functions are derived. Here, as I explained, the second circuit draws energy from the first one, and hence its individual transfer function is not valid when it's in cascade, right? Or to summarize, here in this system, the second circuit produces a loading effect on the first circuit, and therefore this standard formula of two systems in cascade, that G1 times G2 is equal to G1 G2, does not hold. Is the only thing we need to be careful of. Okay, so to conclude, we have seen a lot of nice properties here. We know how to derive transfer functions, how things just become some nice algebraic relations by just deriving the relation between the input and the output. We derived several examples coming from different domains. In the next lecture, we will look at how can we use transfer function to analyze few more properties of the systems. We'll start by defining the concept of stability. That's coming up in the next lecture. Thanks for watching.